All right, you guys, big day. We're starting chapter 5. What this chapter is about is trigonometric identities. And so a couple of these things in these boxes might look familiar to you, but what we're going to do is probably make note cards involving these identities so that you can practice them and have them memorized really solidly, just like we did unit circle stuff. And I'm probably also going to have you put these identities on the back of your unit circle that was on colored paper so that it's handy, easy to grab, and while you're memorizing these things, you'll be able to pull it out and look at it and verify before you continue. But we have this thing called an identity, and what it is it's an equation like this one that should look familiar to you. We're going to talk more in depth about where these equations come from and why they are what they are. You just have them memorized, but you probably don't know why or what they're for. This is the chapter that they're for. And it's an equation that's satisfied by every value in the domain of the variable. So it's always true, basically. Here's an identity. This is another one using tangent and secant. This is one with cotangent and cosecant. These are the reciprocal identities that you already have memorized. And remember, you can switch those. Tangent is 1 over cotangent. Cosine is 1 over secant. Sine is 1 over cosecant. This is a new one. Tangent is the same as sine over cosine. I want to give you a reason why that is true. Sine over cosine, let's think back to what we already know about unit circle stuff and ratios. So sine theta over cosine theta is equal to, remember what the ratio is for sine? It's y over r. And the ratio for cosine is x over r. And remember how to divide fractions? You keep the top one and you flip the bottom one and multiply. And so then the r's cancel here when we're just multiplying. And we get y over x, and y over x is tangent. Okay, so that is why sine over cosine equals tangent. You can do the same exact manipulation with the cotangent one. I won't, in the essence of saving time, I won't actually show that one, but it's similar. You just take the ratios, divide, flip, and multiply, and it equals the cotangent ratio. So these Pythagorean identities over here, Pythagorean kind of makes me think a squared plus b squared equals c squared. And back in chapter 1 when we did this, these memorizing of these equations, I showed you why this one was what it was. And it's similar for tangent and cotangent. So what you can do is you can go back to your chapter 1 notes if you're curious where those come from. It comes from Pythagorean theorem. And that's why they're called Pythagorean identities. Anyways, next thing I want to talk to you about is these negative angle identities. So these are something new, and these are something you're going to want to memorize. There's going to be a lot of true, false, multiple choice types of questions on our tests and quizzes about these. But I want to give you an example and an explanation in terms of why those are the way that they are also. So I'm going to take this sine of negative theta situation and why it's equal to just negative sine of theta. So I want to give you one example. Do you remember what the sine of 45 is? So the sine of 45 degrees, if you remember what that looks like, it's our 45, 45, 90 triangle. It's radical 2 over 2. And remember how we actually do that one? The degree, the theta, is right here. So what if I wanted to do negative theta? Then it would be down here, right? So what's the sine of negative theta? So the sine of negative 45 degrees. Well, the sine is the y value, and the y value is negative down here, right? So the only difference is that this is negative radical 2 over 2. So what I want to draw your attention to is when I have an angle, if I make it negative, the sign switches from positive to negative. Or if the sign was already negative, then it would switch to positive. So that is what happens with sine of negative theta. It becomes negative sine of theta. That's where that one is. Let me show you the cosine one, and then we'll actually move into some examples. Let me show you why that one is the way that it is. What if I did cosine of 45 degrees? So remember how that one is radical 2 over 2? The reason for that is same picture. It's the x value, radical 2 over 2 at 45 degrees. What if I did cosine of negative 45 degrees? That's down here, right? And what's the x value? Oh, still positive. So basically what I'm saying here is for this identity, if you switch the angle from positive to negative, nothing happens to the actual cosine value. And that's why. And so these things you don't have to have memorized, although you probably should at the beginning, but I want you to be able to just think about them. And if you forget, I want you to be able to draw a picture like that so that you can reinforce what the identity is trying to tell us. So these negative angle identities are something that you should probably memorize at the beginning. Think about it in terms of what I explained over here, but we'll be able to apply those later on when we get to one of those examples, okay? Regarding this identity right here, I want to give you an example. There's other forms of the identities that you need to be able to memorize, or to recognize, I should say. So we already know that sine squared theta plus cosine squared theta equals 1. But what if I moved this term over to the other side of the equation? That would mean sine squared theta equals 1 minus cosine squared theta. That is the same identity. It's just rearranged. Or I could also move over the sine squared theta if I wanted to, and I could just have cosine squared theta equals 1 minus sine squared theta. My point in talking about all of these is that this is all the same identity, but rearranged, is what I like to call it. You might have to rearrange some stuff to recognize these identities, okay? So same thing with tangent squared plus 1 equals secant squared. You could move this 1 over to the other side by subtracting it from both sides. It would still be the same identity. Same thing over here. You can move cotangent squared over to this side and just have 1 equals cosecant squared theta minus cotangent squared theta. There are manipulations of those identities that you need to just be aware of and be watching for, okay? Let me show you a different example. This should look a little bit more familiar to you, but I want to show you that if the tangent of theta is negative 5 over 3 and it's in quadrant 2, I find it useful to actually draw a picture of that in quadrant 2. And so remember that tangent is y over x. And if you're confused on which one is supposed to have the negative sign with it, is it the y, is it the x? It's hard to tell when it's written in a fraction like that. Well, in quadrant 2, the y values are positive and the x values are negative. So that helps you figure out where the negative is supposed to go. This is negative 3, this is positive 5, and if I do 5 squared plus negative 3 squared, that gives me radical 34 by Pythagorean theorem. Okay, so stop and pause the video and actually work that out if you can't do it in your head, but you're taking a squared plus b squared and then square rooting that number to get the hypotenuse. So then I can answer this question secant theta. So remember, that's r over x. So in this case, the r is radical 34 and the x is negative 3. But I think it's much easier to do that question while looking at a picture. Okay, so same thing over here, sine theta. Remember, that one's y over r. So the y value in this case is 5. The r value is radical 34, but we do need to rationalize that. 34 doesn't break down, so that's your final answer for that one. Okay, so this third one, cotangent of negative theta. So that, actually I'm going to look up here at my little identities cheat sheet thing that we're going to end up putting on the back of our unit circle. So if I make the theta negative, that just makes my cotangent actually negative. Okay, so I'm going to look over here and figure out what my cotangent is, and then I'm just going to pop a negative sign in front of it because it's negative theta, not regular theta. Okay, so one way that I'm going to look at this is I'm going to find the cotangent of regular theta from this triangle. So the cotangent is the x over the y, so that's negative 3 over 5. But that's just for cotangent of regular theta, the theta that I originally drew in my picture. So in order to answer the question cotangent negative theta, by the identity up here, I just need to take my cotangent answer, which is this, and put a negative sign in front of it, basically switching the sign. So it equals positive 3/5. Okay, I want to show you an alternate way to look at that problem real quick. Remember this picture over here that I drew? So this represents positive theta, and you know how negative theta would put you in quadrant 3? Well, that makes it a negative 5 here. And so the cotangent of negative theta, which is over there, that would be x over y, so positive 3 over positive 5, which is, in fact, 3/5. So another way to think about that is to redraw the picture using negative theta instead of positive theta, but that gets a little bit confusing. So I do want to reinforce that we are going to be using these identities up here. It's faster and more efficient, but again, these identities actually come from somewhere. What you can do is actually draw the negative angle into your picture and figure it out that way if you get confused. Okay, next section, rewriting each expression in terms of sine and cosine and then simplifying. So one trick to simplifying these types of problems is to take whatever functions you're given, in this case tangent and cotangent, and I am going to switch them by using the identities from the box up here. Sorry, I keep flipping back and forth, but this is what tangent equals, sine over cosine, and cotangent here equals cosine over sine. So that is where these are going to play in. The directions tell us to first rewrite each expression in terms of sine and cosine. So basically do a translation of all the other functions using only sine and cosine. So I know that tangent theta, what I wrote above, is that is equivalent to sine theta over cosine theta. I'm going to keep my plus sign in the middle, and I'm also going to rewrite cotangent. That was cosine theta over sine theta. Okay, so this is kind of weird, but now that I have two fractions, I can't add the fractions together unless they have the same denominator, right? So think back to in Algebra 2 when you did a lot of stuff manipulating and making common denominators. What I need to do is make sine and cosine in the bottom of my fraction so they have a common denominator. In this case, I'm going to multiply by sine theta. And whatever you do to the bottom, remember you have to do the top. That's how you make a common denominator. So sine cosine is in the bottom of both of my fractions. So now that they are both the same denominator, I can write them as the same denominator, sine theta, cosine theta. And what I'm going to do is just add everything in the top. And so what's interesting or a little bit different about trig is that we don't write sine theta squared. We actually write it as sine squared theta. And I'm going to keep the plus sign here in the middle. And then this over here is just cosine squared theta. Just a little bit of a different way of writing it, but it means sine theta squared, or sine theta times itself. Okay, so now that I have this, are you recognizing this as one of the identities? Sine squared theta plus cosine squared theta equals, that's just an identity. Okay, so I'm going to switch the entire numerator just to a 1, and I'm going to keep it over sine theta, cosine theta. Okay. And then technically the last step is that it's not considered completely simplified if you have a fraction with 1 in the top. 1 over sine theta is the same as cosecant theta. Remember those reciprocal identities? Look at the top of the paper. And 1 over cosine theta is the same as secant theta. So I'm going to write my final answer, which is 1 over sine theta is the same as cosecant theta, and 1 over cosine theta is the same as secant theta. And that is as simple as I can get. So the simplified version does not have 1 over a bunch of stuff. It is actual like whole functions instead of 1 over two different functions, okay? So let's go ahead and simplify 1 over sine theta to cosecant theta and 1 over cosine theta to just secant theta. Okay, last one I want to take a look at is this one over here. This one is actually much more simple, but the directions tell us to first start by rewriting everything in terms of sine and cosine. And I do know that cotangent theta, look up at the top if you're still unfamiliar, cosine theta over sine theta is a way of translating that. And there's no plus sign in the middle here, so it's multiplication, this times this. And I'm just going to keep my sine theta right there. I'm just going to bring it straight down because it already is in terms of sine and cosine. And then what do you notice here is that we can cancel our sine theta. So this entire thing simplifies to just cosine theta. And that's not a fraction, it's not in the denominator, it's just in the numerator, so cosine theta is my final answer. So I will stop there, you guys. I'll save the next two to do in class tomorrow as a warm-up, but what I would advise you to start working on and start thinking about, maybe drag out your unit circle from the previous chapters that we've been working on, and I would flip it over onto the back, which is probably blank, and start putting these down, because we're going to add more and more and more things and identities and properties and formulas to this chapter, but these you need to start thinking about memorizing, okay, because it's going to help you with the identities later on. Thank you for watching. Hope you had a great night, and I'll see you tomorrow.